Okay, so what we're actually going to do is we're going to go through the pre-lab questions together. So you can double check your pre-lab questions and you can transfer them into your lab notebook if you haven't yet. And then we're also going to set up the data and observation section together because there are lots of data tables. So we'll actually set up the data and observation section together. This lab is not the most exciting in terms of collecting data. The biggest thing with this lab is all the calculations that we do after, which is why we're doing a lot of the calculations together. But for the lab, I had recorded it last week, I think. So we're going to actually you'll just get the data from the procedure video. So that's how we're going to do this lab. And then you'll have time to actually watch that procedure during class time today. So we're going to start with pre-lab questions. And so what I'll do is I will answer pre-lab questions in our lab notebook. So I didn't do purpose and procedure in here, but hopefully you have your purpose and your procedure already done. Purpose of the lab you can find in the experiment overview. So in the lab handout itself, there's always lots of really good information in the background. You get lots of equations that are going to be really useful. And then this experiment overview always has the purpose. You do not have to write the whole thing, only part of it. So you just paraphrase. So then I'll just start with the pre-lab questions. And remember, on the first page, you should have experiment number, the title of the experiment, and the date that you start it, and at least your name. Since we're just watching the procedure, you don't have to put your lab partner. So, but you do need on the first page, experiment number, title, date, and your name. On every subsequent page, you can just put your name. Don't forget, before you turn it in, you should also always sign and date the bottom of every page. So just keep that in mind as well. So for the pre-lab questions, I'm looking at page 2 of the lab, so back of the first page. And there are actually 5 pre-lab questions. There are 4 on this page, and then there's 1 on the next page. We're going to go through each of them so you can make sure you have the correct answer with the pre-lab. So for number 1, it says define delta H of reaction. So delta H of reaction is the enthalpy. So we'll go ahead and we will just answer number 1. So remember, for pre-lab questions, you don't have to write the question out. You're just answering it. So number 1, delta H reaction. So delta, it means change in. So we'll say it's the change in enthalpy of a reaction. And in parentheses, I'm going to say heat absorbed or released. I'm just going to say kilojoules per mole, just kind of as a reminder. All right, it's measured in kilojoules per mole. So pre-lab question number 1, delta H reaction is the change in enthalpy, or it's the heat absorbed or released in a reaction measured in kilojoules per mole. Number 2, define specific heat. So 1 and 2 are just definitions. So 1 and 2 are just looking at definitions. For number 2, specific heat. So if we think about the units for specific heat, joules per gram degree Celsius, specific heat is the amount of heat, and in parentheses I'll put joules, required to raise 1 gram of a substance by 1 degree Celsius. Because your units for specific heat are joules per gram degree Celsius. And so specific heat is the amount of heat required to raise 1 gram by 1 degree Celsius. So 3, 4, and 5 is where we get into the math. So 3 and 4 are solution calorimetry questions, similar to what we looked at yesterday. So in number 3, it says the specific heat of a solution is 4.18 and its density is 1.02. The solution is formed by combining 25 milliliters of solution A with 25 milliliters of solution B, with each solution initially at 21.4 degrees Celsius. Final temperature is 25.3. Calculate the heat of reaction, assuming no heat loss to the calorimeter. Use correct sig figs. So this is a solution calorimetry problem. We know that it's solution calorimetry because it says we are mixing 2 solutions together. So in a solution calorimetry problem, we always have 2 focuses: Q reaction and Q solution. In number 3, it says assume no heat loss to the calorimeter. So that means we don't have to worry about Q cal. So Q reaction plus Q solution equals 0. It wants us to actually just calculate Q. So it says heat of reaction, but it says Q. So I'm going to solve for Q reaction. I don't have to worry about switching it to delta H. We're just solving for Q. So that means I'm going to leave Q reaction alone. Q solution I can plug variables in for. Q is MC delta T. So we'll have mass of solution, specific heat of solution, and delta T equals 0. So over here off to the side, I'm just going to show some of these calculations. Mass of the solution. Like yesterday, when you mix 2 solutions together, you have to use the density to go between the volume and the mass. In this problem, we are combining 25 milliliters with 25 milliliters. So we have 50 milliliters total of solution. That's just from the problem. I added solution A to solution B. Now it's not just the density of water. It's not just 1 gram per milliliter. It's a little bit different. So I'm going to use the density as a conversion factor. Density lets me convert between grams and milliliters. So I want milliliters on the bottom so that it cancels. I want to go to grams. Density, in this case, is 1.02 grams for every 1 milliliter. So 50 times 1.02 is 51 grams. That's our mass of solution. So Q reaction is what I'm solving for. Mass of solution, 51 grams. It says that the specific heat of the solution is 4.18 joules per gram degree Celsius. And then delta T, I'm going to put over here. You don't have to show the delta T calculation. I'm just showing it so that way we remember. Delta T is always final minus initial. And so final was 25.3. Initial was 21.4. 3.9. There's our delta T, 3.9 degrees Celsius. So here we're calculating Q solution. So I'm going to do 51 times 4.18 times 3.9. 831.402. So based on our given information, I'm going to use 831 joules equals 0. So then to calculate Q reaction, we just move it to the other side. Negative 831 joules. Right, if you did negative 830 for 2 sig figs, that's fine as well. So this is using the idea of Q reaction plus Q solution equals 0, plugging everything in. Now number 4 is just slightly different. So I'm going to move this up so we can still see number 3. Prelab question number 4 says, in question 3 above, the calorimeter has a heat capacity of 8.2 joules per gram or joules per degree Celsius. If a correction is included for the heat absorbed by the calorimeter, what is the heat of reaction? So now the problem is telling me, instead of just Q reaction plus Q solution equals 0, we're going to have Q reaction plus Q solution plus Q cal equals 0. Now we look at this and we're like, oh man, we're going to have to do all that work again. But we actually aren't. We know that, again, we're solving for Q reaction. We just calculated Q solution right here. We did MC delta T of the solution. We know what that answer is. MC delta T of the solution is 831 joules. We just have to calculate Q cal. Remember that Q cal is C cal delta T. So again, if we solve for Q reaction, Q solution we've already solved for. C cal, it tells us in the problem, is 8.20 joules per degree Celsius. Delta T is always the same. Whatever the delta T is for the solution is also the delta T of the calorimeter. So 8.2 times 3.9. This is 31.98 joules. All right, when I multiply these two together, that's 31.98 plus 831. So if I keep it to 3 sig figs, 862.98 is going to round to 863. So Q reaction plus 863 joules equals 0. So now Q reaction is negative 863 joules. So number 4 is actually more like what the example was yesterday that we looked at. In yesterday's example, we had reaction, solution, and calorimeter. So if the calorimeter does actually absorb some heat, the reaction will release 863 joules. Okay, so then we have one more question, so I'll be able to fit it right down at the bottom. Prelab question number 5 says, if the reaction in question 3 is A plus B yields AB, and molarity of A is 0.6, molarity of B is 0.6, calculate the enthalpy of reaction, so delta H, for the formation of 1 mole of AB. So now what we want is we want kilojoules per mole of AB. That's what this is asking for. Kilojoules per mole of AB. Now something to think about. The molarity of A and B is the same. The volume of each solution was the same. It was 25 milliliters of each. Since molarity and volume is the same, moles are the same. So something I'm just going to write down first is that moles of A equals moles of B. That means there's no limiting reactant. Makes it very nice for us. And based on the balanced equation, it's 1 to 1 to 1. That means whatever the moles of A and the moles of B are is also the moles of AB. So that's going to be useful because if I find the moles of solution A or the moles of solution B, that's the same as the AB solution. So that's going to make it easy to find moles. So here's what I'm going to do. I'm going to remember that molarity is moles over liters. Molarity is moles over liters. It doesn't matter which solution I pick. They're the same. Both of them had a molarity of 0.60 molar. That's X moles. We need liters. If you look back at question 3, it was 25 milliliters of each. So just a quick reminder down here that 25 milliliters is 0.025 liters. If you remember that, you don't have to write that down. I'm just writing as much down as I can just to help us remember. It has to be in liters to plug it in. So 0.025 liters. So if I multiply these two, 0.6 times 0.025, 0.015. So it's 0.015 moles of A and B and AB because it's a 1:1:1 ratio. So now it wants kilojoules per mole. That's what delta H is. So I'm going to take my Q. I'm going to take my Q and I'm going to put it in kilojoules first. 863 joules is how many kilojoules? Divided by 1,000. All right, so 863 divided by 1,000 is 0.863. All right, 0.863. So Q reaction is negative 0.863 kilojoules. I just put it in kilojoules first just to make it a little bit easier. If you're not familiar, you don't remember the conversion, 1,000 joules is 1 kilojoule. So here's Q. If I divide by moles, that puts it from Q to delta H. So if I do negative 0.863 divided by 0.015, delta H of reaction now becomes negative 57.5 kilojoules per mole. So to go from Q to delta H always wants kilojoules per mole. So delta H is always going to want kilojoules per mole. And to do that, we take our Q, which is in joules, convert to kilojoules, so divide it by 1,000, and then we divide by moles. What we looked at last week is we always had grams on the bottom because they gave us grams. And then we just converted using molar mass. We did that mole conversion. We just kind of did it off to the side at the same time. So these were the pre-lab questions. You could double check your answers. If you have to fix any of them, you can. But I wanted to make sure that we went through them. These are very similar to the calculations that we're going to look at tomorrow and Thursday. So any questions on pre-lab? Let's see. I don't see any for them either. Okay. So the next thing that we're going to do before you guys collect data is we're going to actually set up the data and observation section. because I want to make sure that you're labeling everything appropriately so that way you're not missing any points for formatting. So I finished pre-lab questions on this one page. So I'll go to the next page for data and observations. Now, if you do your data and observations down the side, that's fine. You can just fit everything like on one side. You'll be fine. The biggest thing with this lab, if you look at the data and observations section, which starts on page 5, I tried to include lots of information, kind of like off to the side. You'll notice here what I did is I started labeling the data tables. This has 4 data tables in it. Every data table needs a number and a title. So like this, data table 1, part 1. Down here, data table 2, part 2, reaction 1. Your next one would be data table 3, part 2, reaction 2. So I want to go through and just kind of look at how this would look. I'm going to work all the way across on the page. If you do your data and observations down this one column, then you just work down one column and flip the page when you need to. So all of your temperatures, data tables, always go in your data and observations section. Okay, everything always goes in your data and observations section. Now we're going to be doing a lot of data tables, so if you need a ruler, you can come up and grab a ruler. If you're like, I can draw straight on the lines, then that's fine too. I'm going to use a ruler because even when I try to draw on straight lines, they're not very straight. So if at any point you think you need a ruler, you can just come up. They're right up here on the front table. So for the data and observations, we're essentially going to take what is in the handout and transfer it to the lab. So I know it says part 1 data table, but we're just going to label it part 1 because we'll label all of our data tables appropriately. So I'm going to start by labeling this part 1. Determination of heat capacity. Again, if you're going down one column, keep going down one column. That's fine. I'm just working across. We are just going to transfer what we see over. So the first thing is initial temperature. So initial temperature. And then we have 50 milliliters H2O at room temp. I'll put a line. 50 milliliters of H2O heated. I'll put a line. And I'm paraphrasing some of it too, condensing some things together. But this is where we are going to put all of our data and observations. We have to make it really easy to find everything because we're going to be using a lot of this information in the calculations. So then it comes to the first data table. So it says mixing data, but you're going to notice I labeled this for us, data table 1, part 1. So 1, 2, 3, 4 columns. And if instead of making 4 columns, you just put it all in like 2 columns, so you just do all the time and all the temperature, that's fine. You just need to make sure you have like from 20 seconds to 180 seconds. 1, 2, 3, 4, 5, 6. Okay. So now I'm going to start by labeling this data table. So data table 1, part 1. Every single data table needs a number and a title. When I say number, I mean it needs to say data table 1 or data table 2, and then you give it a title as well. So I'm going to use a ruler because I can't draw lines very straight. I'm probably making my data table way bigger than it needs to be, but it's okay. So time in seconds. temperature in degrees Celsius. Yeah, this will be fine. Time in seconds. And temperature in degrees Celsius. Also, mine's not going to be as even probably as it should be. 1, 2, 3, 4, 5, 6. Okay. All the way across and down. All right, so then I can go through, I can draw my other lines. Is it going to be even? Probably not in terms of like number of boxes, but I'm not picky about that. And if you actually, instead of like putting lines, you know, for every single time, you could just do like this. As long as it looks neat, you're okay. The point of using a ruler is just to make the data table itself look neat. 160. Oh yeah, that would bother me. I didn't do it on this line. Oh well. All right, so then you have your data table. And the data table will get filled in while you watch the lab. It's really not an exciting lab. We're not really missing out on much by not doing it in person. It's part 1 is mixing hot and cold water together. Very exciting. And part 2 is mixing 2 clear solutions together and recording the temperature every 20 seconds. Also riveting. It's the calculations that are the most important for this lab. The specific heat of a metal lab was the better one to do in person, and unfortunately we didn't get to. So there's data table 1, part 1. And then if you notice underneath the data table, we have 2 temperatures, Q and C. So I'm going to just go ahead. I'm going to actually just list them straight across. So T mix, degrees Celsius, put a blank. T average, degrees Celsius, put a blank. Q cal in joules, blank. And C cal, blank. Also, didn't think about how far I was drawing the lines, but again, that's okay. Our data and observation section is going to be very thorough for this lab. So that's just part 1. And if it helps to kind of put like a star for part 1, that way it's easy to find part 1. And then we want to put a star, part 2, determination of heats of reaction. Then we'll go through. Notice for part 2, show you this really quick. For part 2, it says reaction 1 gives us all of the information. Reaction 2, right up here, gives us all the information. Reaction 3 gives us all the information. We do want to split it and make sure that we can tell from each reaction. So I'll start by putting reaction 1. And I'll write out the reaction just in case we need it. NaCl, H2O. Then we'll go through just like before and we'll put initial temperature. We'll draw our data table and then we'll include the variables at the bottom. So initial temp, 50 milliliters, 2 molar HCl, put a blank. 50 milliliters, 2 molar NaOH, put a blank. And then it comes time for another data table. The data table is the exact same as the first data table. All the data tables are going to look just like this, except it's a different number and a different title. So let's see if I can draw this one a little bit better. I'll label it first. Notice I actually tried to label it for you in the lab. Data table 2, part 2, reaction 1. So data table number 2 is the data for part 2, reaction 1. So see if I can draw this straight. And then 1, 2, 3, 4, 5. Oh, perfect. Okay, mine's going to go all the way to the bottom of my page. So I'm just drawing the outline of my data table. You have the option of drawing the outline like this or drawing a line for each part of the data table. That's your preference. So I'm going to do this. All right, so I'm going to have my heading at the top. So I'll have time and temp. 1, 2, 3, 4, 5, 6. Time and temp. All right, so then that's our second data table. And then you're going to do the same thing for reaction 2 and reaction 3. The only difference is that you'll have data table 3, part 2, reaction 2, and data table 4, part 2, reaction 3. So 20, 40, 60, 80, 100,
Miss Mama,
40, 160, 180. So there's reaction 1 of part 2. And then for most people, they'll have a page that looks just like this, except you'll have reaction 2 at the top, reaction 3 at the bottom. So we did the first two together. So then for reaction 2, you want to make sure that you label this so we're ready for data table 3. So this would be data table 3, part 2, reaction 2. And then down here, data table 4, part 2, reaction 3. Oh, I forgot to put the numbers at the bottom. All right, we have these 3 values down here. Oh, nuts, I'm out of space. I'll just do it over here. So we'll have T mix in degrees Celsius, T reaction in joules. So like these numbers, I would put underneath the data table like I did these up here. I just ran out of space. And then we'll have delta H in kilojoules per mole. So again, these 3 numbers would go underneath my data table. If I would have moved this up 1, I would have had space. And so then, again, you'll have data table 3 with your title, data table 4 with your title, and then that will get drawn in your data and observations as well.